Hello everyone, we are Team 2 presenting our final presentation of dueling double deep Q-learning with recursive neural network. The paper will start with the introduction of the paper, replication improvement process, related works, contribution of the project, improvement approach, methodology, results, evaluation, and discussion. If you look at the right, there is a tree, which is a recursive neural network. And we applied this algorithm in the dueling double Q-learning, which had already applied with the state value and actual value. So the dueling network architecture for deep reinforcement learning was our paper, and this paper was on the algorithm related to a Q-learning. Dueling architecture is an architecture to improve the performance of the Q-learning, and it is like using both state value and actual value, unlike other algorithms which uses either one. There are some related works of the deep Q-learning. The first paper, playing Atari with deep reinforcement learning, is a first deep learning model to successfully learn control policies directly from high-dimensional sensory input using reinforcement learning. And the model is a convolutional neural network trained with a variant of Q-learning, whose input is raw pixels and whose output is value functions, estimating future words. The second paper is deep recurrent Q-learning for partially observable MDP. This paper investigates the effects of adding recurrency to a deep Q network, DQN, by replacing the first post-convolutional fully connected layer with a recurrent LSTM. The resulting deep recurrent Q network, also capable of seeing only a small single frame at each time step, successfully integrates information through times and replicates DQN's performance on standard Atari games and partially observed equivalent featuring flickering game screens. Something we can notice about the second paper is that there are some papers which uses recurrence in Q-learning, but our improvement plans, our contribution was using a recursive neural network in the deep Q-learning. So please notice that. The third one is about deep reinforcement learning with double Q-learning. This paper shows that the recent DQN algorithm, which combines Q-learning with deep neural network, suffers from substantial overestimations in some games in the Atari 2600 domains. So it shows that the idea behind the double Q-learning algorithm, which was introduced in the Tableau settings, can be generalized to work with large-scale function approximation. The fourth paper is prioritized experience replay. In this paper, the framework for Google develops a framework for prioritizing experience so as to replay important transitions more frequently and therefore learn more efficiently. They use prioritized experience replay in deep Q networks, reinforcement learning algorithm that achieved human-level performance across many Atari games. The last one, but not the least, the Rainbow combining improvements in deep reinforcement learning. This paper examines 6 extensions to the DQN algorithm and empirically studies their combinations. The paper's experiment shows that the combination provides state-of-the-art performance on the Atari 2600 benchmark, both in terms of the data efficiency and final performance. So the next one is about the progress presentation and the results, which will be presented with Andrea Finazzi.
Hi, I'm Andrea Finazzi. I'll present you our replication and improvement process, and finally the contribution of our project. So firstly, during the progress presentation, we presented our results at that time, which were 2 implementation of deep Q learning and double deep Q learning in Carpool environment in OpenAI Gym. They were both successful in training the agent. So we presented also our work plan for the next period. Firstly, we wanted to focus on dueling DQN and the combination of dueling DQN with double DQN, along with prioritized experience replay. So we combine together all these three algorithms into one D3QM framework, which will serve as the baseline for our next study. The main part of our project is the one in the yellow box, which is the implementation and evaluation of recursive neural networks in this context. So this will be the main topic of the next sections. Our recursive D3QN implementation were tried in two different settings. The first one is our implementation A, which sees two different networks combined together to finally compute the key value, which is our main goal, of course. The network in the blue box you see here is a single input D3QN network, which takes and preprocesses all the state information and then feed it into the recursive network, which is the one in the yellow box. This recursive network recursively computes and combines the state information with the previous layer key value to finally compute a key value useful to train the agent. This implementation, as you see in the plot, was successful in training the agent in our lunar lander. But in the next section, we will see our results in deeper detail. So our second implementation, the implementation B, used a slightly different approach in the sense that a single recursive D3QN is trained, but it is split into two different sections. The first one pre-processes the states information into a state encoding, which is called R in this graph, and then a second layer, which is a classic Dealing double layer, computes the final Q value. As you see in the plot here, we still need further investigation into this implementation because it doesn't succeed training the agent. So to summarize our contribution, the contribution of our project, we focus on the influence of different states in the past on our reinforcement learning agents training. We apply prioritized experience to play in this context, and most importantly, we study, explore, and apply the concept of recursive neural networks in this D3QM framework. How well we did that, you will find out in the next section, where my fellow Wokyung Che will present you the results of our implementation.
I will present the result of the project. First, the implementation of the paper itself, which is implemented with Naive dual-link double deep Q network, was successful as everybody has expected. Therefore, we set this to the baseline of our project and compared it with different recursive neural network versions. In the recursive D3QN implementation A, which is a recursive dual-link double network, is trained along with the standard single input dual-link double Q network. As we mentioned earlier, the agent was successfully trained and the performance of it was not bad, and in some cases it converges slightly better than the D3QN. I will show the comparison graph in the next slide. On the other hand, in the recursive D3QN implementation B, which is a recursive dual-link double network alone, is trained fails to the agent. I think more implementations and studies with this version are required. This is our comparison of the D3QN with a recursive neural network. We represented the red one to the D3QN without recursive neural network, which is our baseline, and the blue one to the D3QN with recursive neural network. We trained it for 3,000 episodes, and in order to compare not only the final performance after the agent is trained, but also to compare the convergence, we plotted the cumulative score during 3,000 episodes. The final cumulative score shows that the performance of D3QM with recursive neural network had similar performance with the baseline, and the curve shows it could have slightly faster convergence speed than the naive D3QN in some cases. And I'm gonna show you the recorded video of the both D3QN with a recursive neural network in the environment of lunar lander in OpenAI Gym. First one with a recursive neural network, and it shows that it is trained well. And the next D3QN with recursive neural network, yeah, it also has trained well, and as you can see, they both have trained well. Lastly, evaluation and discussion. Even though the reinforcement learning assumes that the present data implies all values of past data, we thought the recent data right before the present data can affect the performance of the Q-learning. So we focused on utilizing the past state data on Q-learning, and therefore we implied recursive neural network. In that sense, we thought recursive neural network could be applied to the state continuous environments such as lunar lander and CARTPOL. As a result, we concluded that it seems like a good trial to apply techniques in sequential data processing, such as text-to-speech and natural language processing to reinforcement learning. This concludes our presentation, and thank you.